Hi guys, weather's warming up, spring is coming, and we just had our vernal equinox, or the first day of spring. On the first day of spring, we have an equal number of hours of daylight and darkness. So if there's 24 hours in a day, that means that there were 12 hours of daylight and 12 hours of darkness. You'll learn more about that in a few years when you take earth science. But today, we are learning about forces. You just spent 6-7 weeks doing a STEAM project. I absolutely loved getting people's videos, watching the presentations in class. I was really impressed with the creativity and the tenacity that you guys had to get through those projects. So bravo. Next week at my live Zoom lesson, I will be announcing the winners of the Tim Hortons gift cards. Those are the people, not only who they had all the pieces to their puzzle, but they were creative, innovative, and they just sold me on funding their project. So back to this week. This week, we're going to tackle forces. If you have Mr. Cannon for technology, he spent a little bit of time teaching Newton's laws of motion. And so right here, I'm taking a look at my class page for this week. It says, these are Newton's 3 laws of motion here. There's a lot of text going on, so I'm kind of in the middle. Law number 1 states, an object in motion stays in motion, and an object at rest stays at rest unless acted upon by an equal and opposite force. So I'm sitting in my chair right here. If I'm not moving, if there's no force acting upon me, I'm going to continue to just sit here in my seat. But if one of my kids came tearing in the room and ran into me from behind, boom, I'd go flying forward. So I stay at rest. If I'm at rest, I stay at rest until acted upon by an equal and opposite force. However, if I was in motion and running across the lawn, I could stay in motion until, say, my dog comes running at me and trips me. The dog would be the equal and opposite force. Well, it's not really an equal force, but she would be an opposite force. So we're going to look at that again. Law number 2, force equals mass times acceleration. What that means is that it's going to require more force to get a larger mass moving and moving fast. It's also going to it's also going to need more force to slow down that larger mass. Quick little example, think about an empty shopping cart. Empty shopping cart's easy to zip through the store. As you add items to that shopping cart and it gets heavier and heavier, or it has more mass, it requires more force to push that thing down the aisle and to make those turns. And Newton's 3rd law says for every action, there's an equal and opposite reaction. So if I have an object right here and I come along and I smack into it, an equal and opposite reaction would be that hand was smacking back. Now, it doesn't mean the hands go like this back and forth. Instead, this object is stationary. This object hits it. The moving object feels the force of the stationary object pushing back. So to kind of reinforce those ideas, I have a PhET simulation, and it's phet.colorado.edu if you ever just want to play around with lots of different simulations. You can either click right here on the red highlighted click here, or down below. It's also right on your class page. So let's take a little look here. I'm going to do the click here. And now I'm looking at forces in motion basics. I click on that. It's going to bring up my PhET simulation. Oops, gotta reshare that. So it brought up my PhET simulation, and I'm going to take a look here at the very first one, the net force. A force is, by definition, a force is a push or a pull. Acceleration is the rate at which you're speeding up or slowing down. Acceleration can be a positive or a negative force. So I'm just going to start with, we've got these little blue people here. I'm going to take a small blue person and I'm going to put the small blue person at the end there. I'm going to click up here in the upper right hand corner on the sum of the forces and the values and the speed. Right now, I've got two arrows, one green, one brown, both say 50, and the letter N stands for newtons. Newton is the unit that we use to measure a force or a push or pull. So you push or pull here with this 50 newtons. So this little blue person over here has a net force that is pushing or pulling, in this case, 50 newtons to the left. If I hit go, we can make a prediction about where that cart is going to go. Kind of makes sense, right? It got pulled to the left. I'm going to keep watching them. We can see the speed. The speed was increasing and woohoo, blue wins. It took a total of 50 newtons to get that thing moving, and its speed or its acceleration increased because once you got that thing moving, it doesn't continue to need the same amount of force to keep it moving. If I want to balance this blue person over here, am I going to pick a little red person, a medium red person, or a large red person? Let's see. If I take a medium red person and put them on the end, the medium red person who's going to, we're going to assume that that medium red person's going to have more mass. Sure enough, when we take a look at the sum of the forces, or let's look at the individual net forces, the blue person's pulling to the left with 50 newtons. The red person's pulling to the right with 100 newtons. More mass is going to give you more force, meaning more push or pull. So thinking about Newton's laws of motion, an object at rest stays at rest. Object in motion stays at motion unless acted upon by an equal and opposite force. Right now, this cart is at rest. If I want to put it into motion, I've got to hit go. What we see is the red person with more mass is going to have more force. And that person has 50 newtons more force than the blue person, because the blue person only had 50 newtons and the red person had 100 newtons. Let's return them here. If I want to balance these forces, obviously, what would I have to do? I'd have to have a red person who had an equal force. So I can put that red person on the back, just the same distance that the blue person is. When I hit go, nothing happens. That object is going to remain at rest because there is a force pulling to the left and pulling to the right that are equal. Okay, nobody has a stronger force to set that thing in motion. So if I pause it, do you think it has any kind of impact if I move the red person closer? Oh, take a look. They still have the equal amounts of force. So the sum of their forces is 0. When I hit go, they're not going to go anywhere. So play around with that a little bit. Also down below, you can see, I can click my screens and I went to the bottom and I can click on motion. So I take my little weird robot person, I apply a force, which is a push or a pull, and I'm going to push, and you can see I'm pushing with about 100 newtons. And if I quickly jump to the other side, I had to, and I try to stop this thing, I can see my positive and negative newtons going back and forth as I try and stop that thing. Looks like I haven't stopped it yet. Oh, still moving. So back and forth, you can play with this one a little bit. Okay. There's also a friction. Friction's an interesting force. Friction happens when you have an object pushing down on the earth. Okay, there's that whole equal and opposite reaction. The force pushing down now, there's going to be a frictional force pushing back up. And friction is going to require more force. You have to overcome that friction. So you can play around with friction. And then the last thing you could play around with is the acceleration. And remember, acceleration is going to be speeding up or slowing down. And we use force to create that. So there's a worksheet that goes with this that you can open up. It's right on my class page. Play around with that PhET, fill in the worksheet, and pop it into my Dropbox. I look forward to getting everybody else's little videos or in-person presentations from you as we wrap up that STEAM project. It looks like this year's STEAM fair is going to be the second Tuesday in May, which will be the same day as the budget vote for the school. I'll be printing your posters out on really big paper. And we'll be setting them up either in the gym, the hallways, the aux gym, along with your prototypes that you made. So if you are fully virtual and not coming back to school, if I dropped off your prototype for you, I'll probably ask you if we can swing by and pick that up for the STEAM fair so we can put it out. STEAM fair always comes along with fantastic prizes. And if you're fully virtual, I might be tempted to set up your videos that you've sent to me so when the judges come around, they can get an idea of your presentations. So, all right, I miss you guys. Have a good week.